Welcome to Lesson 13E, Spray Towers, Part 2. Today we're going to finish deriving the grade efficiency equations for spray towers, and then we'll do an example problem of a real spray tower. One thing I did was change all the A's to AC, where C means cross-sectional area, just to distinguish between other capital A's that we use for various things. So that's a minor change to the equations, but we derived these equations 1, 4, and 5 last time. I apologize for this square funny thing there. That's some kind of error translating from Word to PDF. So this is our spray tower. These are our equations. Let's continue analyzing these equations so that we get an overall efficiency for the spray tower. Let's plug equation 5 into equation 4. I get this equation, and then I can do a little cleaning up with the pi's there and these AC's. But recall that this UA times AC is equal to QA. Also recall that VC, what we called VC, was the absolute reference frame speed of the drops, and that was equal to VTC minus UA, which means that VC plus UA equal VTC. And so this is just VTC. The 6/4 becomes 3/2, and then we have all the remaining terms here for d eta. Make sure you don't confuse eta d with just a plain eta. This eta is for the overall spray tower, and this is the single drop. Now recall equation 1. This is our differential equation for mass concentration change, which is just equal to negative of this equation I have up here, negative d eta of dp. So we get dc over c equal negative 3/2 eta d of dp, VTC over VC, QS over QA, DZ over DC. By the way, just a comment here about the way I've arranged this. Notice that I put all the common terms together. Here's a speed over a speed. Here's a volume flow rate over a volume flow rate. Here's a length over a length. And so I can tell immediately that this equation is dimensionally correct. This is non-dimensional and this is non-dimensional. Everything else cancels. So that's a useful hint to do in lots of things that you do later on in life. Well, this is a simple ODE because for a single particle diameter, everything here on the right-hand side is a constant. Of course, the constant changes as we change particle diameter, but remember, we're doing this for one diameter at a time. So for this particular diameter that we're talking about, everything here is a constant. So we can integrate from z equals 0 to z, or c going from c in, that's the inlet at the bottom, to cz. I just want to point out that we're doing this in general for some elevation z here. We're going to really care about L, the whole tower, eventually, but we're deriving this equation for any location z from the bottom towards the top of the tower. We integrate from c equals c in to c dc over c, that's the left-hand side, and then we have our negative sign outside. We integrate from z equals 0 to z of everything on the right-hand side with the dz separated there. That's the right-hand side integral. And as I said, this is a constant at some dp of interest to us. So this integral is just natural log of c minus natural log of c in. And the integral on the right is just the constant times z. So we get that expression. Use our math skills to rewrite this as natural log of c over c in. Then we take exp of both sides, and finally we get then c at any z is c at the inlet, exp of all this stuff in brackets up here times z. I forgot my negative sign, so I corrected that. So this is just exp of negative everything in the brackets times z. I'm going to write this in a more standard form where we put all this stuff on the bottom. So this is also equal to then cn exp bracket negative z over all this stuff in brackets to the negative 1, just the reciprocal. So that's the mass concentration at any z location, or in terms of the grade efficiency up to this location z. We can finally write this out as 1 minus exp of this whole quantity negative z over that term in brackets reciprocaled. So I have 2 over 3 and vc over vtc, etc. from up there. It's just the inverse of that, or the reciprocal. And now we can do something to make our life much easier. And that is, let's define everything in the denominator as LC, the critical length. Alert readers may remember that we've had critical lengths before. This is actually a critical height, but we call it a critical length anyway. Why is that useful? Well, now we can write eta of dp, the grade efficiency, is 1 minus exp negative z over LC. And now finally I'll set z equal L so that we're doing the entire spray tower, not just to some arbitrary location z. So our final expression is eta dp is equal to 1 minus exp negative L over LC, where LC is everything I have circled in blue there. So this is the spray tower grade removal efficiency. Nice and clean here. So the procedure would be that we have to use Calvert and England and SLIN to get A to D. You know how to do that. You have to calculate your VT, the terminal settling speed of the collector drops, the raindrops, and calculate these other parameters. You know pretty much everything else there. Calculate LC, and then we plug into this equation. What's really cool is this is exactly the same expression that we had previously for well-mixed settling in horizontal ducts. We just have a different expression for LC this time. So we expect an S-curve as usual, just like we had previously. And again, I think I mentioned this before, this is typical of most air pollution control systems that are well-mixed and turbulent. When you plot eta as a grade efficiency in percent, we typically get some kind of an S-curve. But because of Brownian motion, this SLIN model, this will tend to have kind of a gap, and then it'll start to go up again later for very small particles. Now let's do an example. This is a design problem. We're designing a counterflow spray tower. We have the following properties. We have a collector, drop, diameter. I did the calculation by iteration for this. You should be able to duplicate that. Cross-sectional area, supply, water, flow rate. So that's being broken up into tiny little drops. Each drop is 150 microns, but the total adds up to this volume flow rate of water falling down. We're interested in 1 micron particles, density of the particles, the air volume flow rate coming in at the bottom. The dusty air contains all these 1 micron particles. We're doing air at SATP for convenience here. You should be able to program this for any temperature, any diameter, any area, whatever we have here, you should be able to solve. So let's calculate the required height of the spray tower to remove 90% of these particles. You know from a previous lesson that we can calculate the single drop collection efficiency A to D as a function of dP. I used Calvert and England and SLIN models like we've done before. 150 micron raindrops, 1 micron particles, SATP, plug all that into one of your previous software packages and you get 1.820%. Now let's use the equations we just derived today. Once you get all that, the rest is pretty simple. So just to refresh your memory, we were talking about a spray tower with some L that we want to determine, where we have the dusty air coming in at UA, and then it's coming out. QA is the volume flow rate of that air. AC is the cross-sectional area of the tower. And we have the water coming in, QS, through all these shower heads. So the water drops are falling. The dirty air with all these particles is moving up, and then we have all the equations we need. So first thing I need to do is calculate UA, which is the airspeed coming up. That's just QA over AC, the cross-sectional area. So I use this area and this QA, and I get 0.3184 meters per second. Now I can calculate the absolute settling speed of the drops in our absolute reference frame. So these drops are actually falling at VC in this absolute reference frame. Well, that's VTC minus UA, so I get that. Remember, if this turns out to be negative, you're in trouble because those drops won't be falling. They'll just be splattering up against the top of the tower, which would be a very poor design. Wouldn't work. Now let's plug in our equation for LC. 2/3, plug in QA and QS, plug in my VC from what I just calculated, divided by VTC, DC in meters, and then A to D, not as a percent, so I had to divide by 100 to put that as a number. And by the way I did this, you can see that the units cancel out very nicely here. All we're left with is meters. I get 9.835, which is our LC, the critical length. Now the overall grade efficiency of the tower, eta, as a function of dP, is 1 minus exp negative L over LC. I set this as the known. Our L is the unknown. This was our requirement to remove 90% of the particles of this diameter, which happens to be 1 micron. So I have to solve for L, do a little bit of algebra. I get this equation as my answer in variables, and then plugging in the numbers, I get 22.6 meters. So our final answer is L equal 22.6 meters. And just a comment, that's really tall. You can imagine a 23-meter column, pretty high up there. May not be feasible. You may want to look into a different kind of APCS, but that's how the numbers came out in this example. Now I'm going to do a little bit further with this example. We're going to call this the required. But let's suppose that all you have room for or all you have money for is 8.50 meters tall. So for that case, let's calculate eta for our same particles. Of Of course, we're going to expect our answer to be less than 90%. Since this tower isn't big enough to give us 90%, this is the value required to get 90% removal of these 1 micron particles. So we have a much shorter tower. I get 57.9%. As always, anything in an EXP has to be non-dimensional, which I check here. Finally, let's repeat this for a range of dP. I used Excel. For this particular case, L equal 8.50 meters and 150 micron drop diameters, but I did actually 5 different drop diameters. And here's how the grade efficiency looks for 5 different drop diameters and a full range of particle diameters. So as we discussed before, this range here is due to our C&E model, and this stuff down here for small particles is due to the SLIN model where it comes up again. And there's always that range where we're not doing a whole lot of removal. Let's do a sanity check for our 150 micron raindrops and 1 micron. I go up to the red curve and you can see that it crosses at 57.9%, which is what I got up here. Finally, I'll make a little comment here that if you want to get rid of particles in the 1 micron or so range, we want the smaller drop diameters, gives you better performance. But unlike the single drop collection efficiency results, in this case, the smaller drop diameters also give you the higher removal efficiency, even for the very small particles. So that's kind of opposite to what we found with just the single drop collection efficiency, which goes to show you that all this stuff doesn't really add up linearly.
But dude, how do you control the size of the water drops, man?
Good question, Joe. Does anyone else want to take a crack at this?
Does it have something to do with the shower heads?
That's right, BJ. You can adjust the pressure and the size of the holes, etc., to make the shower head produce droplets of various sizes.
Cool. Thanks, dude.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.